Welcome back to Neural Intel. Today, we're diving into a fascinating technical development for large language models. It's this concept called sleep time compute. It's based on some recent research from Letta and UC Berkeley.
Right. You shared that paper, and it's pretty intriguing, this idea that models could use their um, inactive periods,
Yeah.
their downtime,
Yeah.
to sort of get ahead.
Exactly, to pre-process information, potentially leading to, much faster and cheaper answers later on. So our mission today is really to unpack the technical details. What's under the hood here, and what could it mean for AI efficiency?
Yeah, precisely. It's not just a small tweak. This could be a really significant shift in how we think about large-scale AI computation. Getting similar performance, maybe, but with way fewer resources used when you actually ask the question.
Okay, let's dig into the how and why. We'll start by laying out exactly what sleep time compute is, then, why they're proposing it, and look at the experiments they ran.
Sounds good.
So let's get straight to it. What, in essence, is sleep time compute?
Okay, so at its heart, it's about changing when the heavy lifting happens with LLMs. Right now, you ask a question, and the model does a lot of computation right then and there. At query time,
Which causes delays, right? And
yeah,
costs money.
exactly, latency and cost. The standard approach often assumes you give the model the query and all the context together, fresh, at what they call test time.
Right, like it's starting from scratch every single time. But, as the paper points out, that's not always how it works in the real world, is it? Many applications have context already available.
Precisely. Think about asking questions about a big document you've already uploaded, or a coding assistant that knows the repository it's working in, or even just a chatbot remembering the conversation history.
Hmm.
In all those cases, the model already has access to a bunch of background info. It's not really starting from zero.
Okay, so this is where sleep time compute comes in. It's about using that idle time, the sleep time.
Yeah, exactly. Using that time for the model to do some, let's call it offline thinking,
Mm.
about the context it already has.
Kind of anticipating what might come next.
Sort of. The goal is to anticipate potential questions, maybe, or just to pre-digest the context, pre-compute useful information before the user query actually arrives.
Okay. And this pre-computation does what? It changes the context somehow.
It results in what the paper calls a re-represented context, basically a processed version of the original information. Then, when the user does ask something, the model uses this pre-processed context.
And the hypothesis is this is faster.
Yeah.
Or cheaper.
Both, potentially. The idea is that you get similar accuracy, but you need significantly less computation at that moment at test time. Like doing your homework beforehand makes the test itself less strenuous.
That makes intuitive sense, a potential big win for efficiency. So how did they test this? What kind of technical evaluations did they set up?
Right, they need specific tasks. Tasks where there's a clear context and then a separate question about that context. So they adapted some existing reasoning challenges. They made these stateful versions, stateful GSM symbolic and stateful AMI.
Stateful. So the key is splitting the problem.
Exactly. Taking the original problems and deliberately splitting them. Here's the setup, the context, and then here's the question based on that setup.
Okay, GSM symbolic, that rings a bell. Math word problems, right?
Right.
More complex.
Yeah, derived from GSM 8K, which is grade school math. GSM symbolic adds layers, makes them trickier. They use specific splits, P1 and P2, and just separated the initial problem info, the context, from the actual question part.
Got it. And stateful aim. Aim is harder math.
Much harder. American Invitational Mathematics Examination. These are tough competition problems. They did the same thing. Took problems from recent competitions, 2024, 2025, and split them. Context first, then the specific question.
So for both tasks, the goal was clear. Can the model pre-process the context part during sleep time and then answer the question part using less compute at test time without messing up the answer?
Precisely. They were looking for that measurable drop in test time computation while keeping accuracy high.
Okay, moment of truth. What did they find? Did it work?
The results were, well, pretty encouraging, actually. They found sleep time compute could create a Pareto improvement. That's the term they used.
Pareto improvement, meaning you improve one thing without hurting another. Or maybe improve both.
Exactly. In this case, less test time compute without sacrificing accuracy, or getting the same accuracy with less compute.
And how much less compute are we talking?
They saw about a 5x reduction. 5 times less test time compute needed to hit the same accuracy level.
Wow, 5x.
Yeah, on both stateful GSM symbolic and stateful AIM. That's
Okay.
pretty significant.
That really is. It suggests you could run these things with a fraction of the live processing power. Huge implications for cost and speed. Do they also look at like what happens if you give the model more sleep time, more pre-computation?
They did. They explored scaling up the amount of computation done during that sleep phase. And interestingly, spending more compute during sleep time actually led to better accuracy later on.
Oh, really?
Yeah, up to 13% better accuracy on stateful GSM symbolic and up to 18% on stateful aim.
So more offline thinking doesn't just save compute later, it can actually improve the final result, even if the test time compute is limited.
That's what the results suggest. Is
Yeah.
like better preparation not only makes the task easier, but can lead to a better outcome overall.
Fascinating. It's not just shifting the cost, it's potentially improving the capability too.
Seems like it. And they didn't stop there. They also thought about scenarios where you ask multiple questions about the same thing.
Ah, okay. Like drilling down into a document or a topic that happens all the time.
Right, so that they made another data set, multi-query GSM symbolic. The idea being, if the model did that sleep time work on the context,
It shouldn't have to redo it for every single follow-up question.
exactly, that pre-computation, that groundwork can be reused,
Yeah.
amortized across multiple queries related to the same context.
Makes sense. Did that pan out in the experiments? Did they see savings there?
They did.
Duh.
By amortizing that initial sleep time cost over several related queries, they found the average cost per query dropped by about 2.5 times.
2.5 times cheaper per question on average. That's another substantial saving, especially for interactive use cases.
Definitely highlights the practical value for things like chatbots or analysis tools where you have an ongoing interaction around the same base information.
Okay, so it saves compute, especially across multiple queries. But does it always help equally? Or are there situations where sleep time compute is, more effective than others?
Good question. They looked into that too. Their hypothesis was that it would work best when the follow-up question is somewhat predictable.
Predictable, meaning based on the context, you have some idea what the user might ask next.
Yeah, exactly. If the model can sort of anticipate the likely direction of questioning, its pre-computation is more likely to hit the mark, to be useful.
That feels intuitive. If the question comes completely out of left field, maybe the pre-computation wasn't relevant, how did they measure predictability?
They used a technical measure, the log probability of the question, given the context, calculated using Llama 270B. Basically asking a big model, how likely is this question given this setup?
Okay. And did predictable questions show bigger benefits from sleep time compute?
Yes, the findings lined up with the hypothesis. The accuracy boost from using sleep time compute, compared to just standard test time compute, was larger for questions that the Llama model rated as more predictable.
So if you're in a scenario where the next step is reasonably constrained or guessable, sleep time compute really shines.
That seems to be the takeaway. It gives us a clue about where this approach might be most impactful.
All right, so they tested it on these reasoning tasks. Did they try it on something maybe a bit more applied, like a real-world type of problem?
They did. They included a case study using a software engineering task. It's a benchmark called SWE features. It involves pull requests, code changes that modify multiple files to add new features.
Okay, so in that scenario, what's the context and what's the query?
The context was other related pull requests, like previous changes in the code base that might be relevant. The query, essentially, was the new pull request that the AI agent had to figure out how to implement.
Yeah.
And during sleep time, the agent could explore the code repository.
Ah, okay. And performance. How do you measure success on something like that? It's not just a single right answer.
Right. They used the F1 score. It measured the overlap between the files the agent predicted it would need to change and the files that actually got changed in the correct solution.
Right.
So how well did it anticipate the scope of work?
Got it. And the results. Did sleep time compute help the agent predict the right files?
It did, particularly when the test time compute budget was lower. At those lower budgets, using sleep time compute led to a better F1 score compared to just throwing more compute at the problem during test time.
But maybe not at very high compute budgets?
You noted that, yeah. At very high test time compute levels, the standard approach might eventually catch up, or maybe even slightly edge out sleep time compute, at least in this specific SWE task.
So again, it seems particularly valuable when you're trying to be efficient with your compute resources at the moment the task needs doing.
Exactly. Letting the agent do some homework, some repo exploration during sleep time, helps it perform better when it actually tackles the pull request, especially under computational constraints.
Okay, so we've covered the core idea, the stateful reasoning tests, the multi-query benefits, this predictability factor, and even the software engineering case study. It definitely seems like a technically solid and promising direction.
I think so too. It's a clever way to leverage that often unused time. The potential for significant cuts in test time compute, the cost savings, faster responses, that's all very appealing. And the fact that investing more in sleep time might even boost accuracy is also, well, really interesting.
Yeah, and that amortization across multiple queries feels very practical for real systems.
Absolutely. Of course, it opens up new technical questions, right? Like, how do we get really good at predicting what pre-computation is actually going to be useful? That seems key.
Right. And how do you weave this into complex back and forth conversations where the context is constantly changing?
Yeah, integrating it seamlessly is a challenge. And, you know, could the stuff generated during sleep time be useful for other things,
Hmm.
like representation learning, or maybe even generating synthetic data? Lots of possibilities there.
Definitely food for thought. For our listeners who want to dive really deep into the technical nitty-gritty, the paper is on ArcSiv. The ID is 2504.13171V1, and the code and data are up on GitHub, linked from the paper under Leta I.
Yeah, definitely worth checking out if you're interested in the implementation details.
So yeah, this deep dive really shows some exciting technical innovation aimed at making these powerful LLMs more practical and efficient. Thanks for joining us on Neural Intel. And remember, for more deep dives into AI and ML research, check out our webpage links in the bio.
And maybe one last technical thought to leave folks with. Given that predictability seems so important for maximizing the benefit, what kinds of technical architectures or maybe clever pre-processing could we design specifically to get better at anticipating likely user queries within a given context? How do we technically boost that predictability to make sleep time compute even more effective? That's a fun technical puzzle for the future.